The law of large numbers. The law of large numbers applies to a process for which the probability of an event and the results of repeated trials are independent. So basically what this is saying is the more times you experiment, the more times an event is repeated, the process is repeated, the more likely of you getting closer to the theoretical probability. And so here's a situation with a die rolling. The probability that you get a 1 out of the 6th, you see it starts out really low, and here's the theoretical probability here, 0.167. But as you do more and more trials, then you get closer, that pink line gets closer and closer to the theoretical probability. A roulette wheel has 38 numbers, 18 black numbers, 18 red numbers, and the numbers 0 and 00 in green. Suppose that all possible outcomes, the 38 numbers, have equal probability. I don't think they do, but I've never played roulette, so yeah. What is the probability, if they're equal, of getting a red number on any spin? So the probability of a red would be the number of reds that there are over the total number of possibilities. There's 18 reds and 38 possibilities, so the probability would be 0.474. If patrons in a casino spin the wheel 100,000 times, how many times should you expect a red number? Well, if it's that many times, then you should expect a red number about 47.4% of the time, or 0.474 times 100,000, which is 47,400 times you would expect to get a red. Consider two events, each with its own value and probability. The expected value is this. The event, for the value of the first event times its probability, plus the value of the second event times its probability, and so forth. Suppose an automobile insurance company sells a policy with an annual premium of $200. Based on data from past claims, the company has calculated the following probabilities. There's a 1 in 50 chance that a policyholder will file a claim of $2,000. A 1 in 20 chance that they'll file a claim of $1,000, and a 1 in 10 chance that they'll file a claim of $500. Assuming that the policyholder could file any of the claims above, what is the expected value to the company for each policy sold? Well, the first event is that the company gets $200, and the probability of that event is 1. Because there's a 100% chance that you're going to pay the company for its policy, right? Then there's the possibility that the company could lose $2,000. Notice how I put a minus there. And there was a 1 in 50 chance that they could lose $2,000. There's a 1 in 20 chance that they could lose $1,000, and a 1 in 10 chance that they'll lose $500. If you put all that together, you get $60. the company can expect to make $60 off the policy. The gambler's fallacy is the mistaken belief that a streak of bad luck means a person is due for a streak of good luck. False. Suppose you are playing the coin toss game, in which you win $1 for heads and lose $1 for tails. After 100 tosses, you are $10 in the hole because you flip perhaps 45 heads and 55 tails. The empirical probability then is 0.45 for heads. So you keep playing the game because theoretically you should get ahead half the time, but you're wanting to get it more, right? With 1,000 tosses, you get 480 heads, so you've gotten closer to half, and 520 tails. Does this result with the law of large numbers, and have you gained back any of your losses? So it does agree with the law of large numbers because you're getting closer to half. 480 is 48% of 1,000, while 45 was just 45% of 100. So you are getting closer. But the proportion for the first 100 losses was 45%, and the proportion for the second 1,000 was 48. Okay, so it agrees because you're getting closer to 50. After 1,000 tosses, you have won $480, but you've lost $520 for a net loss of subtract $40. So your losses have now increased despite the proportion of heads growing closer to 50%.